Good morning, Bulldogs. I don't know if you can sense this, but I'm kind of excited about today. Yes, I was once like you, wondering why do people get excited about least squares regression? By the way, that's what we're doing. I don't know. I think it's part of grad school. It's part of learning more complicated methods of doing similar work. But at some point, it does almost turn into an old friend. There are definitely limitations, and we'll talk about that. There are pitfalls, but all in all, it's a pretty robust way to estimate a relationship. And it has a lot of things that you can do to modify it, to make it more appropriate for a problem. Like usual, we're going to have a little introduction. We're going to talk about fitting and interpreting the model, evaluating a model, categorical predictors, inference for the multiple regression model, interaction, and model selection. We need to be able to assume that we can fully specify this model, meaning that we know what causes this thing we're measuring or this thing we're examining, and that we can measure that and then use those inputs to find out what we need or find out what these coefficients and their standard errors are. And rarely is that done with a single variable. We're going to need to use more than one variable, which kind of begs the question, if you haven't thought of it yet, how do we do this? We've already got our 2 dimensions of a graph on paper, and we're going to introduce more? Yep, we sure are. And it's going to be great. Again, what we have is a response variable or a dependent variable, an intercept, that's your B naught, plus your B1 X1 plus B2 X2 plus blah, 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 BP XP. Those are all of our explanatory variables, our independent variables. There are several applications of multiple regression. 2 we're going to discuss are estimating association between a response variable and a primary predictor of interest while adjusting for possible confounding variables, and constructing a model that effectively explains the observed variation in the response variable. Just so you know, if you want a job where you can make good money doing something simple, it's estimating prices and demand at those prices using this very method. Let's look at an example. Statins are a class of drug widely used to lower cholesterol. If followed, recent guidelines for prescribing statins would lead to statin use in almost half of Americans between 40 and 75 years of age, and nearly all men over 60. A few small studies have suggested that statins may be associated with lower cognitive ability. The PREVEND study collected data on statin use as well as other demographic factors. You can imagine that this is a difficult problem to sort out, because if more people of those ages are on statins, well, that's also an age where cognitive ability tends to decline. So there's that. It might not be the drug. It might just be age. It could be a lot of other things. It could be some of the other drugs that many elderly people take. I say elderly. I'm almost 40 myself. Oh, look at this plot. That could be a problem. Look at this. I mean, they both, cognitive ability has a downward slope for both those who use and those who don't. Blue dots, by the way, are non-users. Red dots are users. That could be a very similar slope. Or maybe the statins do make someone more susceptible. It's maybe they were on that road. Who knows? But good news is we've got some tools to try to figure this out. Here we have our box plots, and this is not definitive at all. It looks like statin use is a little lower. It's definitely a smaller box, top to bottom, but they overlap. The interquartile ranges definitely overlap. Okay, so now we have results. And if we were to just use the statin user 1-0 binary variable, so 1 yes, 0 no, this would be our result. And we'd have an intercept, so that would mean that on average we would expect a non-user to earn a 70.71, and we would expect the statin user to earn about 10 points less. But like I've alluded to, we have not controlled for age here, and that could be a confounding variable. So again, we can do better. We can control for age with this model. And let's give that a whirl. And if we estimate that model, we have our score is a function of statin, so it's binary 1-0, and plus age, so that's our continuous independent variable. Our coefficient results are 1.37.882. That's our intercept. That means the average non-statin user, regardless of age, is 130. That's their score, what we would expect. And then we have our 1-0 binary statin user variable. And that says 0.8509, meaning that when we control for age, now a statin user will score higher, on average, 0.8509 points. We even changed our sign. Now we see the age obviously has an effect, or at least probably has an effect. We don't have a statistical significance in this answer yet, but it looks to have a negative effect, as one should expect. The great thing about the software is that it provides this nice table of results, because we need to know what the standard errors are. We need to know what the standard errors are so that we can calculate t-values. Well, because we're going to use a t-test to find out if any or each of these variables are statistically significantly different than 0. So we're going to test a hypothesis test. This is a t-test, testing if the beta is anything other than 0. Our intercept is statistically significant, but that doesn't really mean much. Then the statin user. We don't get confused by this engineering notation. That's not significant. Now, what about age? Age is statistically significant. So, the statin user relationship doesn't seem to be any different than 0. We're essentially going to extend simple linear regression to multiple linear regression. We still have to have linearity, so these variables have to be linearly related. We need constant variability. We need independent observations, and we need the residuals to be approximately normally distributed. We can't scatter plot beyond, like, could scatter plot 2 variables. Then you have a very difficult, and it's computer animation at that point, it's 3-dimensional. It's be very difficult to interpret. But then you get any further than that, and you can't illustrate, you can't do a scatter plot. So what we can do is we can plot each of the variables independently and treat that as a ceteris paribus relationship. So holding everything else constant but the one variable in the graph, then how the one variable in the graph works. So we can, again, use the R-square to evaluate how much this model informs us. In this case, we're explaining about 28.5% of the variability of the dependent variable with these two variables, or these two explanatory variables. That's not great. That's not really even good. Sometimes it's the best you can do, but it's not good overall. Similar to R-square, there's another measure, adjusted R-square. And what adjusted R-square does is incorporates a penalty for using predictors that don't contribute much. Because if you just keep adding variables, you can get oftentimes to an okay R-square, but it doesn't necessarily tell you anything. So adjusted R-square has a penalty for adding stupid variables. We can take this further, but before we do, let's quickly review. The mean RFTT or RFFT score for individuals not using statins is 70.71. And we know now that the mean for individuals using statins is 10.05 lower than those not using them. What about more variables? We didn't do a very good job with age. Maybe we need more variables. And for the record, this process of adding variables to try to increase R-square, this is absolutely not the way you do this. You define your model, what you think is important. You estimate your model, and what you have is what you have. You do not go looking for R-square. Well, presumably education would have something to do with the score of cognitive ability. So let's add a variable. And let's see, there's already a variable in this particular data set. And they code it as 0 primary school, 1 lower secondary school, 2 higher secondary education, 3 university education. So wait a minute. 0, 1 thing made sense because if it's 0, then that coefficient doesn't enter into the equation because you're multiplying the coefficient by 0. If it's 1, you're multiplying the coefficient by 1, so you're going to, again, lower your score by whatever this coefficient is. But what about 2? Does that mean that 2 is twice, 3 times? It's multiplicative, or what is this? Yeah, we're going to cover that in just a second because this is not going to work. So this is a little more of a clear relationship. I think we can say that education probably does have an impact. We'll have to see with some testing, but this is more the difference between the primary ICR or IQR interquartile range and the university. They don't even overlap. So this could mean something. But again, we have to test to look. Test to know. The first thing we have to do is recode this one variable into a variable for each level. So you're going to have a 1, 0 for education lower to second. You're going to have one for education higher second and education for university. Now you will note that I did not include primary. It's because that is our baseline. So that's if all of these are zeros, then we have the primary is what we're comparing against. There are also some mathematical reasons why we don't include all of them, but I'm going to let that one lie for right now and probably for this entire class. The coefficients the resulting coefficients from fitting this model with all of these dummy variables are an intercept of 40.94. So our average primary educated person's RFFT score is 40.94. The first dummy variable, so that'll be the next up level of education, is education lower second. So if this person has that education level, that's a 1, and it's going to be, that means that the education or the RFFT score will be 14.77857 points higher than the primary education. And we can see at the bottom of the slide there that that's exactly the case. The primary education mean is 40.94 and the lower second is 55.71 or 9, thereabouts. Now so we do this again and again. So it's 30, the education higher second is 32 greater than primary. So we see 40.94 again plus 32.13, and we're going to get something in the neighborhood of 73. And university education, 44 points higher, almost 45 points higher. Again, 40.94 plus 45 points almost.